Now, how or why we need to construct reinforced earth embankment or reinforced earth slope? Your normal slope, when you construct, you cannot construct steeper than a particular slope, 1 in n whatever value. You do slope stability analysis and let us say you find this is your slope. Now if you try to make this slope steeper, this will collapse. There will be failure like this or this, whatever type of slope here, you can have it. But by reinforcing the slope, you can make very steep slope, like you can see in this case. This is the reinforcement which is provided here, and it is wrap around sort of thing. And then you always provide a protective facing. I will tell you the reason why we provide protective facing. So you can construct steeper slope than what otherwise you would have constructed. This is reinforced earth slope, and in its maximum case, this can be as steep as 90 degree, vertical, almost vertical. Here you have constructed almost vertical embankment like this, and then this is the protective wall. We'll see this actually not a wall, this is just a small facade. So this is the wall. This is reinforced earth slope, and this is reinforced earth wall. Okay, now, so as we see, the side slope can be made steeper and near vertical by adopting RE technology using geosynthetics. The reinforcement type, we use steel also, we'll see this in detail, but nowadays the most common is use of geosynthetics as reinforcement. The reason we'll see. Now, this structure, especially this, is an alternative to conventional gravity or cantilevered retaining wall. Let us say we did not use the concept of reinforced earth, and you have to construct an ROB or some embankment in area where you don't have land available for constructing a normal slope. What would have been the alternative? We would have constructed a normal retaining wall, which will be very thick, which will be rigid, and it will have a very, very solid and very big base. If you see base of retaining wall, let us say bank is 8 or 9 meter high, your retaining wall base may be as deep as 1.5 meter and wide as 3-4 meter, very massive, and this is a rigid structure. Whereas this is an alternative to whatever gravity or cantilever retaining walls we make. Now, what is the advantage? First advantage is in areas having scarcity of land, this reduces the cost of project and project completion time, because you don't have to acquire this much of land. Nowadays land is very costly, so you can save that cost. Secondly, getting land is a very long drawn process, very, very lengthy process. So that much project time also can be saved. That is first advantage of using this structure. Secondly, it reduces the quantity of fill material, because otherwise if you would have in bank, you will need some fill material here. And this fill material is you take either by quarrying or by mining, which are nowadays again very difficult due to environmental concerns and all. So when you reduce the quantity of fill material, you also reduce adverse impact on the environment, because you reduce the quarrying, and you also reduce the fuel consumption in transporting this material from quarry to here, which is quite significant. So many dumpers, tippers and all, they will come. So that also you can save. And third thing, which is not there but we'll see, is these structures are more flexible as compared to rigid structure. If this is my, let us say, a retaining wall, and if some crack develops here, maybe I will try to do some grouting, this, that and all. But if it does not happen, then repairing this is very, very difficult. Maybe you have to remove this whole thing and then put some dowel here and again construct this. Whereas in reinforced earth wall, it is sort of a modular thing. You can, if any component is affected, you just take out that component or maybe one near to it, and then you can repair it locally also. It is possible to repair it. So that's another advantage of using these structures as compared to normal conventional gravity or cantilever retaining wall. Okay, now we'll see what are various components of a mechanically stabilized earthen wall or reinforced soil wall. This please see it carefully, because this same thing we will use everywhere in our design, and all these terms also we'll be using. First is, let us start from this side. This is your bank which is coming, otherwise normal bank with normal material up to here. This is known as retained fill or backfill. Many times we use small letter B for this in various properties. Retained fill or backfill. This is my normal fill which was there. Now towards the front, this yellow color thing, there, rather than filling with whatever was existing soil, I take a selected soil. This is a selected type of soil, and I put reinforcement in this. These dotted lines are reinforcement layers. There are various reinforcement layers. So this is reinforcement, and this fill is known as reinforced fill or selected fill. Or reinforced fill or selected fill. Now this earth which we are using the reinforced fill has to be a granular soil. It has to be a granular soil for reinforcement action to mobilize. It cannot be cohesive soil, and in various codes properties are given what properties it should have. This is a selected good soil of some width. How much is width we'll see when we go to design part. Okay, so backfill or retained fill, selected fill or reinforced fill. This is foundation soil which is existing there, on which we are building. If this soil is weak, there is a definition what is weak. Then we have to do ground improvement first, and then construct this bank, because otherwise after you construct whole thing there will be settlement. So this is another thing. This is about foundation soil. Now move further. This reinforcement is connected to this front portion, this gray color thing, and this is known as fascia or facing. Fascia or facing. This looks like a wall, but actually it is not wall. It's a very slender section. We'll see what is its function and all. But this is a very, very slender vertical element, and this reinforcement is connected to this. There are various methods of connecting. In some places, some hooks or some other arrangements are provided so that reinforcement gets interlocked with this. In some designs, this reinforcement gets sandwiched between these two rows of fascia, and then it gets physically interlocked, and friction here. There is vertical weight and friction here that gives the, but it has to be held here. It has to be anchored here. Basically requirement is it must be anchored at the end in connection with fascia. So this is facing reinforcement connection or fascia reinforcement connection. Then below this fascia there is a small thing. It is not actually foundation. It looks like it is leveling pad. We'll see its typical dimension. It is a very small pad. Purpose is you make a reference pad which is level so that you can construct this in vertical direction. It provides support and holds this in vertical direction. So this is another component which is leveling pad. And the last component, which is very, very important. In fact, in our railway cases, if I tell you few of the cases, the failure of our RE structure was because of not taking care of this component, and that component is this blue colored thing. This is known as drainage. Many times, because it is a vertical element, it is also known chimney drain. But this is an element which is thrown out vertically right from top to bottom, and then bottom there has to be some arrangement for water to go out from here to outside. Either we put a pipe here and take it, or give outlet here and then it goes out. But water has to be collected, very, very important, from top as well as from this. It has to be collected, it must flow vertically, it must come down, and then sometimes people provide the outlet at different heights also. Sometimes it depends on what is the design, or at least bottom there has to be outlet through it, either it goes out or you provide a pipe here, and through this pipe you take to the end. But this is a must. If we don't provide drainage, then it leads to catastrophic failure. Because what happens is, number one, if you don't provide drainage, there will be hydrostatic pressure on this, for which it is not designed, first thing. Second thing, what happens is, it corrodes rather the fascia reinforced connection, and the so-called anchoring which we have provided gets lost. And because of that, its reinforcing action which was to mobilize along the reinforcement, the interaction between soil and reinforcement gets weakened or gets totally eliminated. So the whole reinforcing action is lost. Third thing, when in the select fill also, when your moisture content increases, the friction between your reinforcement and your soil, what you call interaction or interlocking, that also reduces. So your reinforcement action reduces. Again, it is detrimental to your strength of reinforced earth structure. And therefore, this component, proper provision and proper maintenance of this component is very, very essential. Very, very essential. Proper selection of this fill, proper maintenance of this, they are very, very important. If you see any failure analysis of failure of reinforced earth wall, in fact last Friday, second was Friday, there was a webinar rather, I was also there, about failure of RE walls in India. And many cases, including our railway cases, people had analyzed. A lot of people from academia, from the big companies who supply reinforcement design and reinforcement, the contractors, the consultants, NHAI people, and a lot of people were there. And these are one of the major components of RE wall failures. One is not doing geotechnical investigation. Almost people have stopped doing geotechnical investigation. ये RE wall के लिए क्या investigation की जरूरत है? And this foundation soil starts settling. That is one. Secondly, problem at the connections. That is another one. Third thing, this soil not being proper. Fourth is drainage not being proper, and it has led to collapse of reinforced wall. So they are the essential components of a reinforced. We'll see about them in detail also. Now, if you see the typical dimension, the fascia wall facing, it is 180 mm thick. Typical. Of course, there are different designs. We'll see again. Nothing. It's not actually a wall. It is not a load-bearing wall. It is a facade. It is a fascia, which is protecting your reinforcement and giving it anchorage action. It does some other work also. We'll see. Leveling pad, typical dimensions, 150 mm thick and 300 to 400 mm wide. So this is also, really speaking, not a foundation. This is actually a very small pad. And as I told you, backfill soil, it should be non-plastic granular fill. Then only this interaction between reinforcement and soil will mobilize. Otherwise, if you have got cohesive fill, this interaction will not mobilize. Okay, we'll see the components one by one in detail, but I hope this components, at least prima facie or as a general guideline, now everybody is aware what component of an RE wall or RE structure. Okay? Any doubt or any question in this?
सर एक डाउट है मेरे को एक्चुअली but I am not sure about it. In some lectures I heard that this facing reinforcement should not be connected.
Should not be connected? No, it has to be.
Not in this case. If it is there is no retained fill, entirely reinforced fill in case of whether it is true.
No. It has to be. It has to be connected. It has to. Otherwise, anchorage action will not be there. And if I will, when we go to design, and I will show you the failure mechanism, you will probably appreciate it. It has to be. Otherwise, this will not mobilize the tension, required tension. Okay. We'll cover this when we go to design part. It has to be. There are different type of connection principles. There are patented methods. Different. We'll see that also. But it has to be connected. It has to be connected.
Okay, sir.
Right. Any other doubt? Anybody or any question if you're good? Shall we go ahead then?
Yes, sir.
Yes, sir.
Now, see in brief about these components. What are these components of RE wall, reinforced earth wall? We'll see in detail. So, first let us say reinforcement. Now, what is the function of reinforcement? To stabilize the reinforced fill. Yes, that is one function, because through that only we are mobilizing this reinforcing action. So it is stabilizing the reinforced fill. That is main function. The another function is to support the facing. If this is my fascia, it is a very, very lean structure, just standing on a small leveling pad. Keeping it vertical, or sometimes you give some batter from the vertical, is very difficult. That is also done by reinforcement. Reinforcement keeps in position. It acts like a stage behind the reinforcement, behind this fascia. They act like a stay, and then this our select fill or reinforced fill is there. So when reinforced fill is trying to push it outside, this provides as a counterbalance to this and acts as a stay. So this supports the facing also. That is another function of reinforcement. And what are their desired properties which we look for in the reinforcement? Number one, long-term strength, tensile strength and stiffness. It must have stiffness so that my deformations are minimum, because I don't want wall to lean like this. If let us say I have taken reinforcement and it is taking force T. Now, if this T is less, what will happen? There will be yielding, and if it yields, then wall will start leaning. So I don't want that. Therefore, they are high stiffness. Their stiffness is high, and good tensile strength also. Another important property is long term. Creep effect should be least, because today if I tension it and leave it, it has to remain there, whatever is the life of structure. So of course there is some creep in every material. We will see that also, that effect how we take into account. But it must be as less as possible. Its coefficient of creep should be the least possible. So that is first requirement. Second is interaction with soil. This for friction to convert into tensile strength, the lateral strain to convert into lateral restraint through this, it must interact with this soil. So there must be friction and interlock between this reinforcement and soil around it. That's why number one, you always use granular fill here, because it is more granular, whereas in cohesive fill, this coefficient of interaction is less. Secondly, the surface of reinforcement also should not be very smooth. If your surface of reinforcement is very smooth, then what happens is, again, your coefficient of interaction, which we normally take 0.6, 0.7, 0.8 like that, that gets reduced. So that is second property. Third is connection with facing. As I told you, it must have a proper connection with facing. There are different connection. Sometimes there is a knot, sometimes there is a bodkin element, like from this it comes out and it comes out this bodkin piece you put here. Sometimes you put it between two elements of fascia, and fascia has got some projection which goes into this, and then by friction. So there are different patented or different design connections, but there has to be a proper connection with facing. And another important property from constructability point of view is easy installation. It should be such an element that you are able to install it easily. Quickly, you should be able to install it. It should not be very heavy, should not require very sophisticated machinery and equipments for installing. These are the properties, required properties in reinforcement. And the type of reinforcement, initially reinforcement was metallic. Even now also, at least in railway, I see many places we are using metallic. But otherwise outside people, very rarely they use metallic. In metallic, it can be strips. Metallic strips like this, and their surface is roughened. Some serration sort of thing is there, so that interlocking is there. Bars nowadays very rarely they are used. Previously they used to be sort of bars, or like reinforcement bars. Nowadays weld mesh was used very commonly. Weld mesh like this, and if you see its section, it looks like this. It is because this is thicker, so because of this roughness, it mobilizes more interaction between soil and the reinforcement. Problem with this is corrosion. Number one, and creep. There are still with low creep, but still not as good as geosynthetic. Corrosion is another problem. Over a period of time, it gets corroded. So you have to put anti-corrosion treatment and a lot of other things. So because of that, they have become less popular. And nowadays, most of the time, you will find people use geosynthetics. In geosynthetics, first, for few years, people are using woven geotextile. Now, woven geotextile as a reinforcement is not very common. People don't use it. They use it for some other purpose. But most commonly, geogrid and strips. Let me just, I got some sample. It is with me. I will show you. Yeah. I will just stop sharing for some time and this is GeoGrid. You are all able to see it?
Yes, sir. Yes, sir.
This
Yes,
is most commonly used. This is known as biaxial GeoGrid. So this is one element which is very, very commonly used now. They are biaxial extruded geogrids. Biaxial, so there are various variety. This is made by extrusion principle. So biaxial extruded geogrid, and they come into different basically comes in tensile strength, 50 kilonewton per meter, 80 kilonewton, 90 kilonewton, like that. So depending on what is the design. This is one. And another component which has become very popular in last 5-10 years only, very, very recently, is this. They are known as strips. As you can see, it looks like this. A simple strip, geosynthetic strip. And their surface, if you see, it is rough, so that it mobilizes the friction. And they come in different capacity, like this is for 40 kilonewton, this is 50 kilonewton, this is 75 kilonewton, this is 100 kilonewton. Like different ratings, their tensile strength. So this two type of reinforcement. Now, railway, of course, I still see metallic reinforcement being used, but outside if you go, you will find most of the places, 95 out of the 100 place, you will find this two type of reinforcement. They are most commonly used. Okay, so now I will share the presentation again. So, presentation is visible to you, I think?
Yes, sir, visible.
Yes, sir.
Thank you. GeoGrid and strips, they are most commonly used now. Advantage of them, why they are used is, number one, they are non-corrodable. They do not get corroded. Their coefficient of creep is very, very less, very light, very easy to handle, and you can manufacture them in any strength. As I told you, they look almost same, 40 to 100. If you see the physical appearance, only change in input material and some process. So they have become very popular nowadays. Here if you see, these are the strips. In this case you can see this is the strip type of reinforcement. Metal strips also people use sometime, and it is connected to fascia this side and other side. And so this is metallic strip. This is geogrid in this, and here you see the connection is like this. It is going into this fascia right up to end. Then I will show a video also later on. There is a key below this fascia which goes into this reinforcement, physically interlocks, and then there is a friction also between this block and next layer will come at this block. So this is geosynthetic, mainly geogrid. Geogrid has been used here. Now regarding fascia or facing, what are its function? One function is it acts as a formwork to contain fill during compaction. Now when you are constructing the wall, you put layers of fill material, then reinforcement, then again next layer of fill material, then reinforcement. So for this material not to get laterally go out and collapse, this acts as a sort of formwork. It prevents this material from spreading. Then it also stabilizes fill against raveling, erosion and all. If there is rain or there is some water stagnates here, this will prevent wash out of this material outside. Containment, it provides a containment here. Another important function of this is it protects the reinforcement. See, whether you got metallic reinforcement here, metallic reinforcement, if you leave it open, if you don't put this, because of sun, rain and all atmospheric effects, it will get corroded, and after some time it will lose its connection. Similarly, geosynthetics also, they get degraded by ultraviolet rays. All geosynthetic materials, their degradation is mainly by ultraviolet rays, and the biggest source of ultraviolet rays is sunlight. So when sunlight is there, if you don't protect them, this also will start decaying at the end. Sometimes we provide reinforcement like this also, what is known as geo-wrap. This reinforcement gets decayed here, and after some time this material will fall. So this acts as a protective cover against the reinforcement. And another beautiful thing is, we will see some photos also, this can also provide you very good aesthetics, because this is a factory made product. This fascia boards you make in a controlled environment, in a factory or in a yard, casting yard. You can provide any sort of design. Some of the photos also we will see. You can make it like an art gallery. Otherwise your normal retaining wall will be a drab and some very, very shabby sort of structure, or you put some plaster on that and then it falls, and all those things can be avoided. It can be used rather to provide good aesthetics. And there are various types of fascias. First, which were initially used, were full height concrete panels. Some places it is used even now also, you will see. There your full height, whatever is your height, 5 meter, 8 meter, 9 meter, 10 meter, full height concrete panel, 1 panel, 2 panel like that you will put, and then you will do the work. Disadvantage in them is weight becomes very heavy, and such a tall structure, maybe 8-9 meter also, when you are working and all, keeping them vertical in position and all requires a lot of efforts. And therefore nowadays, normally they are not used. Some places, I will show you, like Japanese railways and all, they use similar sort of thing, but it's a bit different, you will see. Full height panels nowadays are not very common. You will not see, at least in India. Next is incremental concrete panels. Here, these are the concrete panel of 2 feet, 3 feet size like that, incremental. One layer you provide and do earthwork. Then you provide second layer, and these blocks get interlocked with each other, and these horizontal joints are segregated. Then you do next layer earthwork, then provide another layer of block and next layer. They are very common nowadays. In fact, you will find many places this incremental panel, nowadays means last 10-15 years, incremental panel are most commonly used. Handling of them is easy, not very heavy, not very light also, but they are not very heavy, and they are very old. So now there are no patent and all, most of them are non-patented. What has come recently in last maybe 7-8 years or so, and most of them are patented, is what is known as segmental concrete blocks. Here they are very, very small blocks like this. You can lift by hand also, and one layer of blocks you put and you do earthwork for one layer. Then you put your reinforcement, over that you put another block, then do second layer, like that. Very easy to handle. Nowadays you will find they are used very commonly, especially in highways and these places, but most of them are patented. They are still new, they have not become patent free so far. So there are different companies, they have got different patents, and according to them you have to make some changes in your design, or you have to design accordingly. Another thing which is used is gabions. These gravel or cobble filled gabions, wire netting structures, you use them and you physically interlock your reinforcement here. Advantage of gabion is, number one, gabion acts as a drain also. We need a drain behind the fascia, so there you can probably, if you use imaginatively, you can use gabion as a drain also. Second advantage is, many places like somebody has seen in Bombay and all, when you use New Bombay Powai, this Loda Arcade, and there are many places, what people call is a green fascia. In this front portion, some portion you will put some soil also, and then you will grow some vegetation in this soil, good vegetation, and trim it and all. So this whole face will look green always. It gives you a very good aesthetics. They are known as green fascia. In fact, there are many products which are coming like in gabions with green fascia. Terrames, green terrames, various names are there of various companies. So gabions also are used in fascia, more where you need some landscaping and that sort of thing. So these are various fascia systems used. Now here, as we have seen, incremental panel. In first phase you can see these are incremental panel, and this construction is being done using incremental panel. Whereas in second construction, they are this modular small blocks, and construction is done using them. I will show you videos of both, and that will give you a very good idea about construction also, how construction of these type of structures are done. So first, using incremental panel, you're able to see the video. second video is using small modular blocks.
Precast concrete blocks for reinforced soil structures have been widely used globally since the 70s. These are flexible structures and are amenable to differential settlements without show of distress, unlike rigid structures. A reinforced soil structure constructed of soil, polymeric geogrids, and concrete blocks is less expensive and faster to construct and is obviously preferred. After ground improvements, wall construction begins with excavating the foundation, typically 1 meter deep and wide enough for the reinforced
Leveling bed.
A PCC leveling pad of lean concrete is now poured with perfect alignment across the entire length of the wall. The first layer of blocks are laid and carefully aligned on the PCC pad. Now, let us look at the blocks in greater detail. The concrete blocks are uniquely shaped to provide both stability and economy. Significant benefits include cost economy, as the blocks do not require any steel. The hollows in adjacent blocks are filled with gravel, which form stone columns. This contributes to the stability of the fascia. The key at the bottom of the block fits into the cavity of the lower block and firmly anchors the geogrid.
So this is how your geogrid it is mechanically interlocked and then friction between two.
The position also ensures a backward batter. As all blocks are identical, casting can commence prior to design approvals. This reduces dependencies, resulting in speedier execution. After the first layer of blocks, the reinforced soil zone is now backfilled with non-plastic engineered soil and compacted with a vibratory compactor. The first layer of geogrid is placed side by side without overlaps, covering 100% of the reinforced soil zone for a safe and robust design. The geogrid is pulled taut and positioned in place with wooden stakes. The next layer of blocks is now laid. The key, that is an important part of the block, connects the block to the grid, increasing the frictional resistance for a better pull-out value. This is one of the unique design features of the block system. The entire process is repeated, layer by layer, with primary geogrids placed every 3 layers. Based on stability considerations, short secondary grids may also be placed in between layers. When the wall reaches ground level, the filter media is placed behind the blocks. This acts as a drainage zone and relieves the structure of poor water pressure. It is self-compacting require heavy compaction equipment. Thereafter, the retained soil zone is backfilled as per specifications. RCC coping beam is cast along the top row of the blocks to smoothen the steps and align with the carriageway. Now the carriageway is laid. Finally, the crash barriers are placed into position, the pavement is laid, and the medians are constructed. The carriageway is now complete. Summarizing, the main benefits of the concrete block or geogrid system for reinforcing soil structure are as follows. Economy, as it only requires dry cast and does not require any steel. Speed, as it has lower coordination requirements, hence fewer delays. Also, it requires fewer types of input materials, one type of block, and the geogrid, hence fewer outages. And as it is a simple installation, it is an extremely fast construction. Finally, it results in a robust system, as stone columns are formed by gravelin cavities and the presence of secondary geogrids. This provides a perfect phase stability. With 100% grid coverage, it provides a robust design.
Okay, so now I hope you got an idea about how these structures are constructed, a general idea. ठीक है?
ठीक है सर.
Yes, sir.
Okay. These videos and all are there in your that course content folder also. I have copied there. So if you want to see later on in your free time, you can see also. Now, as I told you, this fascia can be used as a medium for improving aesthetics. So these are some of the RE walls for highways and roads. Actual, now you can see. You can make any sort of aesthetic improvement. It is like an art statement. See, this is very simple. This one looks very good. This is good. Say this one. So because it's a factory made, yard casted product, you can put any design, anything there, whatever you want. And fascia can be used as a medium for improving the aesthetics. In addition to embankments, the RE structures are also used as bridge abutments. See, if we see in plan, let us say this is in plan. This is my bank or embankment, and this is my RE structure, and I may have reinforcement like this. And there will be drainage here, and there will be drainage here. Now, wherever, let us say you have got some underpass going through your bank, or maybe it is a bridge, then you will have abutment also somewhere here. Even abutment also, rather than being normal gravity type, you can make it RE, and then reinforcement of abutment will come in this direction, and this will be drainage of abutment. And on top of your abutment, your gutter will be resting, and you have to only put a very far less than our normal, a sort of bearing pad here, and then load is taken. So it becomes like a U structure, inverted U. So RE walls are used for abutments also, and there also same principle applies. You can get economy, and you can make more flexible structure like this. This abutment, this is RE abutment, or this abutment, this one. They are, rather than being normal conventional gravity type abutments, they are reinforced earth abutment. So same principle what is applies here. Of course, the analysis is bit different. Design is little bit different, not much different from the RE wall which we will see today. But you can design bridge abutments also. Now coming to the question of RE walls for railway. Now as far as highway is concerned, even railway, we as railway person might have constructed hundreds for ROBs and many other places. As far as using this RE abutment for railway embankments is concerned, we are a lot apprehensive. Let us accept it. In Indian Railway, we are very, very apprehensive. Probably one reason for that is that we had some failures. For ROB, whatever RE walls we had constructed, in Indian Railway, we had some failure. And some of them were really bad, let me tell you. They brought very bad name to railway. But if we go into that failure analysis, you will find there is nothing wrong with technology or the principle. It was more of either improper design, improper execution, most of the time. Otherwise, with technology-wise, there is nothing wrong. So much also, as I told you, we did not do even geotechnical investigation. I was surprised to see in one case, I will not name the zonal railway, where for backfill material and reinforced fill, they say, let us assume value of C5 and gamma equal to this. This is horrendous, let me tell you. Can you assume in design what is the value of that material? And there is a circular which says we must assume this much. Listen, nowhere it happens like this. Why should we assume? I should go and test it in the lab. There is a very simple lab test for getting gamma, that is density, and for getting C and phi for granular material. You have to do a direct shear test, which is not such a great test when you are spending so much of money. So if we do like this, if we deal the things in such a casual way, then no, there is no way any structure will fail. Why only RE structure? Your retaining wall may also fail, your buildings may fail, your bridge may fail. So with technology wise, there is nothing wrong. Now, yes, that is a fact. People assume this is more of a delicate technology where if something wrong happens, things fall very quickly. It collapses or there is a catastrophe. But same principle applies for your PSC structures also. Same principle applies to your welded structures also. As compared to riveted, our welded girder also, if something wrong happens, it will collapse like a pack of card. But does that mean we will not use welded structures? Whole of the world, including your space shuttles and big ships and cargo ships and all, they are made with welding. We also in railway nowadays, you will see most of our girders are welded. What it requires is to have a proper quality control in welding and proper system that we get a proper product. Similarly in PSC girder also, as compared to heavy RCC, in some cases, not all, it may collapse in a catastrophe. Does that mean that we don't use PSC structure? We are using. So therefore, the need is we must do proper design and proper work rather than being afraid of this. Maybe we start in a small way. Anyway, if you ask me that how many RE embankments have been constructed in railway, the list will be very small. The RE embankment which I know, one is in Katra yard. If someone of you has go to Katra, the other extreme end, other away from station side, there is a very high slope and next to that is a road and some canal going. So if you give normal slope, both road and canal will be covered. There it was provided. Now almost 10-15 years are over. We don't think anything wrong has happened. Now, as the part of currently being constructed USBRL project, at some of the places they had no alternative but then to go for RE. They have done it. In eastern corridor of DFC, at 2-3 places, they have done it. In metros, many places they have done it. So these are the examples of RE embankments for railway loading. That is what I am aware of in India. And as I told you, in 2014, RDSO issued that G18 guidelines for RE wall construction, and then they developed some agitation. So they said, okay, use it for trial for other than mainline. And based on, they said that feedback, we will revise it. And no feedback was received and it was not revised. So this is position as on date. But world over, if we see, RE wall abutments are not uncommon. They are very common. In fact, this is somewhere from America, where heavily loaded trains are run. This is an RE embankment for that. This picture is from Japan, Shinkansen, and in fact in Japanese railway, Shinkansen, which is high-speed train, their system is when your height of bank becomes more than 10 meter or so, means double digit, they go for viaduct. Other than that, less than 10 meter, their default is RE embankment. They construct only RE embankment up to 9 to 10 meter. Normal embankments they don't construct. Number one, because land is a very scarce commodity there. Secondly, there are a lot of paper by RTRI, Railway Technology Research Institute, Japan, and one of their experts is Mr. Watanabe. He keeps on coming to India. Many times we had discussed with him also that there are documented research of RTRI that in case of earthquake, which are very common in Japan, RE embankments are more ductile and more durable as compared to normal embankment. Similarly, in case of tsunami and all, where heavy wave action was there, water has overflown over the embankments and all, there also the performance of reinforced earth embankment was found better than normal embankment. So considering these advantages, they are using. So many places world over, what I am trying to say is RE abutments have been used for railway purpose also. So as such, there is nothing wrong with technology. Yes, some delicacy is involved with this. We must take cognizance of that in our design as well as construction. Now, what they used in Japan, the RE embankments, it's a bit different. What different, I will tell you. How do they construct it? The sequence of construction is like that. First, of course, you do ground improvement and finish this. Then you construct the leveling pad here. And this is the drain hole. Just excuse me 1 second. This is first step. Then what they will do, they take whatever geosynthetic reinforcement they use, mostly geogrid. So they take geogrid, take it like this, and then they use gravel gabions. So they wind the geosynthetic around this gravel gabion and bring it here like this. And this height of gabion is equal to first layer. Normally you do compaction they do in 30 centimeter. In India we do 20 or 25 or so. So this one, then first layer of 30 centimeter is constructed and compacted. Then same thing, again the geogrid reinforcement, and it is wrapped around this gravel gabion and second layer. Like that, one by one, they construct all the layers, and this gabions, they act as temporary retaining structure, so they are able to construct almost vertical face or vertical face. After that, they put a shutter here and do casting of this fascia, precast fascia in one go. So it is one panel, full height, cast in situ, and through this, of course, they have got this drainage outlets at suitable places. So cast in place RC fascia, full height. This is the construction sequence which is followed in Japan. And for integral bridge abutment also, they use 2-3 techniques. For bridge abutment, if you see, this is your girder is coming, this is bearing, okay, this will rest on the fascia. This is very lean as compared to your normal abutment. This fascia is like this, and behind fascia, this is that gravel filled gabions, and this reinforcement, and then in a triangular wedge, they fill compacted, lightly cement mixed gravelly soil. Gravelly soil with some cement, 0.5%, 1% like that. Japanese, that also in Japanese, they use the cement mixed gravelly soil very commonly. In this triangular, And some of the reinforcement, every third layer or second layer, this reinforcement goes up to this triangular edge. Otherwise, this is the reinforced length. So this is how, in general, their design of abutment, RE abutment is there. And if you see their progress of RE works or number of RE abutments in Japan, if you see, this is time, year-wise. In 1982, they started the research at University of Tokyo. And their first RE abutment somewhere here, 1989 or somewhere, they constructed. Now, this line, this is annually, how many they are constructed, this bars. And this is cumulative, how many RE walls they have constructed till date. So up to 2013 or 14, they had constructed 158 number of RE walls, and total length of these RE walls is 160 kilometers. Okay, so around 159 or almost 160 RE walls for railway, and totaling to a length of 160 kilometers. So quite huge numbers, it is not one. Secondly, another thing, if you see this chart, there are some years when suddenly after those years there is a spurt or there is a rise in construction of RE walls. One is here, you can see here this graph becomes steeper, another is here, third one is here, and fourth one is here. What are these incidents? See, they are all major reconstruction events. In 1995, this is year 1995. In 1995, you must be knowing there was famous Kobe earthquake, after which all courts and many things world over, they changed about dynamic analysis and all. And because they found in 95 that RE structures are giving better performance, there was a spurt in construction of RE. Secondly, this is start of reconstruction, this was year 2000, start of construction of HST line, Shinkansen. In between there was some slowdown. From here again they started. So when again they went on high speed, they pushed the pedal for constructing more and more RE lines, RE structures. This point is year 2004, when again, if you recall, the famous Niigata-Kane Choetsu earthquake came. And again they found that in earthquake, performance of RE structure is better. So you can see immediately after earthquake, again there is a sharp rise here in RE structure. And here, this was the 2011 great East Japan earthquake when the tsunami happened and there was a lot of damage, if you recall. Again after that, again there is a sharp rise. So this chart, what does it show? Number one, it shows that even in Shinkansen line in Japan, RE embankment for railway is very common, and every earthquake or such major event, they found the utility of this better than conventional structures, and there was an accelerated construction of this type of RE embankments. But of course with due care and this thing. This is another type of integral bridges which they have used. Now you can see this is your bank, normal bank, and there is an opening here. So inverted U sort of thing box they have given. Its thickness is only 600 mm. See, and foundation also actually is a pad of 0.7 mm. This is going, and below this is only ground improvement by cement mixing, means normal soil, gravelly soil with cement mix, that is for about 3.2 meter width. And this is a single cast thing, and for abutment, this is the reinforcement pattern in a triangular fashion like this. Some reinforcement goes up to end of this triangle, every 4th, 5th or 6th, otherwise this puts. And this is drain. And this is your select soil or reinforced fill, and behind this is original backfill. So now you can see how lean and easily constructible structures Again, they have been constructing using the principle of reinforced earth. A photo of somewhere, say it comes out of tunnel. So this is abutment, which is RE. Just after tunnel, only triangular portion will be there. This is of course normal pier. This is RE abutment and then RE bank. So integral structure from RE abutment, it goes to RE bank.
Sir, one doubt,
Yeah.
sir.
Yes.
Previous slide.
Yes, please.
Previous slide, please, sir.
This one.
This one, yeah.
Yeah.
So actually, in this, the cement mixed gravelly soil is filled in active zone, right?
Cement mixed gravelly soil is
In active failure zone, means resembles that
Here.
shape.
it is filled here. Yes.
In previous, it was different, no? Previous slide.
Yeah. In fact, there are two different design of integral abutments. Here, I will tell you. Yeah. Yes, one. This one. This is used cement mixed gravelly soil as a select or reinforced fill. Okay. In this one, whereas in another one, in next one, here also they have used cement mixed gravelly soil in this triangle. In addition to that, they have used it here also. Basically, idea is in this, what load comes here, to have little bit more bearing capacity of the ground as compared to this, to improve this bearing capacity. So what we were giving as leveling pad, that has been made little bit thicker, and this has been made. This also is cement mixed gravelly soil in this select fill, and here also. Okay.
Okay.
Clear?
Clear, sir. Okay.
Okay. Any other questions or any doubt about or any apprehensions about RE walls or RE embankments for railway purpose? Nothing?
इंक्रीमेंटल आरी सेगमेंट बनाते हैं, उनमें कनेक्शन एक दूसरे में कुछ कैसे होता होगा या कैसे इनकी स्टेबिलिटी होती है?
इसका इंक्रीमेंटल ब्लॉक का की होता है ना दोनों के बीच में. देयर इज ए की बिटवीन, दिस इज वन ब्लॉक, देयर इज ए की हियर दैट गोज इनटू अनदर ब्लॉक. दैट इज द कनेक्शन. इसमें वीडियो में आपने देखा था ना, यहाँ की होती है एंड दिस की goes into reinforcement also, geogrid. So this is the connection between the two blocks. Okay, sir. Any other question? Any other doubt? Nothing? Can we go ahead then?
Yes, sir, please.
Yes, sir.
Even height-wise also, even in India itself, there are many examples of high reinforced earth walls. Not in railway, of course, but outside. This is one which is in two tiers. This is in this national highway between Chennai to Calcutta. This was designed by, I think, Dr. G.V. Rao of ex-IIT Delhi. This is first part and this is second part. This is around 10 meters or something, and or maybe more than. This is also another 10-15 meter. And many years, not one, many years it has been standing okay. There is no problem as such. And you must have heard in last 2-3 years in Sikkim, Pyongyang or Paekyeong airport was made. There they have constructed 80-meter high retaining wall using RE principle, 80, for retaining the pavement of airport. It is a tabletop airport. Then presently Kannur airport almost getting complete in Kerala. It is about to be over. In Kannur airport also same, about 70-75 meter of that range. They have constructed RE walls. So it is not What I'm trying to tell you is we have to take adequate care, we have to take precautions, we must design properly, but we should not be afraid of the technology, that there is something wrong with the technology, and if we do, something wrong will invariably happen. That is what it is. A delicate technology, yes, we have to take adequate care and then do it, but don't be afraid of adopting this technology with due diligence. Okay, now we have got only two things. One is stability of RE walls, and after that, how do we design? So we'll see that. The stability we'll see before maybe break, then we will take a break, and after that we will go to second part. So when we talk about stability of RE walls, basically we talk about two types of stability. If this is my RE wall, this is my drainage, this is reinforced fill, this is my backfill. So retained fill or backfill, this is my reinforced fill or select fill, this is my foundation soil. These are the components, and there will be some load here which is surcharge. Okay, and there will be leveling pad here. This is in general. So when I talk about external stability, let me change the color. I take this as a rigid block. This reinforced fill I take as a rigid block for external stability. Somebody's microphone is on, please mute it. I think it is giving some echo.
Shukla sir.
So this reinforced fill or rigid, you take this as a rigid block, and then you check for various parameters. We will see what are those parameters. That is external stability. Another thing is internal stability. In internal stability, you check stability of only this reinforced element only. Reinforced element and its component reinforcement, their stability. So basically there is two types of stability: external stability check and internal stability check. So first we will see what are those checks, and then after break we will see how they are done. Now therefore when we talk about stability, now let us say this is my initial position of my RE wall and this is a rigid block. So there will be horizontal force on this. From where this horizontal force will come? Because of this. Behind this rigid block, this backfill B is exerting the earth pressure. So because of that earth pressure, it will try to slide horizontally. And what gives the resistance? At the bottom of this, there is some vertical load also V, and there will be some friction at the bottom of this wall. So that will give me the resistance. So I have to check that there is no sliding failure, number one, in external stability check. Second thing, overturning failure about this point. With this point as fulcrum, now again, there is a horizontal force because of this earth pressure from the backfill, which is trying to turn it, and this vertical load is trying to give stability. So there is overturning moment and there is stabilizing moment. So we have to see there is no overturning failure with respect to this. That is external stability. Then because of this, overturning may not be there, but here there will be maximum pressure. If you put the pressure diagram, if you make like this, that pressure here should not be more than the bearing capacity of soil here. Otherwise there will be bearing or tilting failure. So we will check for this also. That is third thing. Fourth thing is, with this whole thing as a rigid block, the whole thing should not slide and there should not be a slope stability failure, or what we call as global slip failure. There should not be global slip failure. So there will be 4 checks: sliding, overturning, bearing capacity and slip failure. These 4 external stability checks we have to do. So this is what we will do. First, for bearing capacity. Now there will be surcharge load, there can be dead load surcharge, there can be live load surcharge, all those things. Then there will be earth pressure because of surcharge and because of this backfill. So this will be shape of my earth pressure diagram, and let us say this is my resultant force P. This resultant force will pass through my base, and you must heard about Meyerhof distribution in soils. If this is my base, and number 1, I divide it into 1/3, 1/3. If L is my length of base, L by 3, L by 3, L by 3, and this is center. So normally number 1 it says it should pass, this resultant should pass in middle third. It means eccentricity. Eccentricity will be from here. So eccentricity should be less than L by 6. That is number 1. Secondly, because of even if there is some eccentricity, your stress diagram will become like this. This is compressive force and this is tensile force. Your soil cannot take tensile force. So this is neglected. You take only compressive force. That's where your Meyerhof distribution comes into place. It says that out of this total length L, if L is eccentricity, you neglect L minus 2E and you assume that your force is acting on L minus 2E length only, and the force divided by L minus 2E, area corresponding to that, will give you maximum stress, compressive stress. So you calculate L, then L minus 2E, and that gives you the maximum compressive force here. That must be less than your safe bearing capacity of this soil. So that is bearing capacity check. We'll actually also see after lunch how this calculation is done. Similarly, forward sliding, the worst case will be when there is no surcharge here, surcharge is acting here, and then you have got earth pressure. So because of surcharge and because of this earth pressure, this will be the earth pressure diagram. You can resolve it in horizontal direction. This will be the horizontal force which will be acting here, and because of shear strength of foundation and depending on this vertical load, there will be resistance to this. So ratio of resistance divided by this, that will give you the factor of safety against forward sliding, and we calculate that we get required factor of safety. So this is the check against forward sliding. Overturning also same thing. This, I divide this force into horizontal and vertical direction. This weight also will have vertical components. So this horizontal multiplied by this lever arm will give me the overturning moment, and these two forces, their moment about this will give me the restoring force. So restoring force divided by overturning force will give me the factor of safety, and the factor of safety should be more than whatever is requisite value. So this is overturning check. And for global stability, we have to take this as a rigid body, take properties of this soil, we neglect the fascia normally and take the surcharge, and then put all these things in a computer program, software, and you calculate minimum factor of safety. There are approximate method also. There are some approximate method. I will just name them. I will not go into those details. There are graphical method by which roughly you can calculate factor of safety. So maybe for initial design, you can use those graphical methods. It is given in RDSO G18 also. But I will always, and most of the designers always in the end, you must check it using a suitable slope stability software. Now coming to internal stability. That was external stability. Internal stability means stability of only this reinforced block. So there are two type of things. Now what will happen? First is what is known as tensile rupture or rupture of the reinforcement. Now these are various reinforcement layers. Okay. Now let us say we are talking about this layer. On this layer there is some vertical stress sigma v at this level. Okay. And if you multiply it by active earth pressure coefficient Ka, this will give you sigma h. This will give you the horizontal stress here. Sigma h will be coefficient of earth pressure times sigma v. This is horizontal stress. Now if I want to know the force, let us say half of this is spacing. So half of the spacing this side and half of the spacing this side. The stress in this portion will be carried by this reinforcement. So this is SV, what we call as effective spacing of my reinforcement. So sigma h, horizontal stress, multiplied by SV will give me the horizontal force. So sigma h is K sigma V. So K sigma V into SV. This is the tensile force in the strip. I have calculated the tensile force in the strip, that this much is tensile force T. And whatever is the design tensile force strength of this reinforcement, that is its strength. So TD by T will be the factor of safety, so that this steel should not rupture. That is first check in internal stability check. And the second check is what is known as pull out or adherence failure. Now here what happens is, this is my fascia. Now whatever we say, but there will be some movement always. This cannot be zero. So once some movement is there, behind this fascia, this your active earth pressure wedge will form. This much area will get loosened. What is shown in this wedge, yellow wedge, this area has got loosened, and this is your active earth pressure wedge line. Now once this has become loosened, the adhesion in this is gone. So if I take any reinforcement, what will be stable or anchored zone will be this. So this wedge, this active force is trying to pull this out, this reinforcement out, and the friction between this reinforcement and this soil is trying to restore it. So the pull-out resistance of any of this, if I take any one reinforcement, so first I have to plot this active earth pressure wedge, and let us say I take this layer of reinforcement, then its pull-out resistance will be, if this anchor length is LE, or many times we also put it LIP. Now on top and bottom, two places it is in contact with soil, so therefore 2 times LE, and tau is its frictional resistance or anchor between this strip and soil. So pull-out resistance will be for this 2 times LE into tau. Now 2 times LE, and frictional resistance will be this frictional coefficient time vertical stress, because your frictional resistance is vertical stress multiplied by this. So 2 times LE, C tan phi. C is coefficient of cohesion, phi is angle of internal friction, into sigma v. So this is pull-out resistance. Now I add pull-out resistance for all the strips. This strip, this strip, this strip, all the strips. That will give me the total pull-out resistance, and total pull-out force will be the force which is exercised by this wedge. And how it is calculated, we will see in the formula. That will be total pull-out force. So total pull-out resistance divided by pull-out force, this should be more than factor of safety. Sometimes we take 1.5. How much is actual values, we will see. So that should be more than my factor of safety for pull-out. So like this, we do 2 internal check. So we do 4 external checks and we do 2 internal checks, and Once all these checks are over, then of course there are many other design. You have to check connection design also for whatever is maximum force coming in, whatever here. This tension will be maximum in this, because the sigma will be maximum at the bottommost layer. So bottommost layer it will be maximum. So for this tension you have to check the connection also, and very minimum sort of so-called check of fascia also. But main checks are these two types only: external stability and internal stability check under both static and dynamic condition. We have to check static, and with earthquake also we have to check, and it must pass the muster in both the cases. Then our design will be correct. Okay. ठीक है? Up to here?
Clear, sir.
Clear. So now it is bit early, because I wanted to cover after tea. If you have got any questions or something, we can discuss. Otherwise, we'll take our break bit early. Tea break, because now only leftover is what forces, what are various factor of safeties and all, how we take them into account. That is the only part left over, design of RU1. So that we will cover after tea. So if you have got any questions, you can ask before we break for the tea. Otherwise we can cover this slide, then maybe break. When we talk about design, as I told you, we basically follow BS 8006. That is the Mother Code World Over Part 1. And it was revised in 2010. And since this does not cover construction and dynamics, so we follow that FHWA code. And for our earthquake coefficient and all, our IS code 1896 or 93, whatever. So this BS 8006, if you read, it is basically a design based on limit state principle. The principle followed in BS 8006 is limit state principle. So we will also follow the same thing. And when we talk about limit state, what limit states is considered is, number one, first is ultimate limit state. So loads and all those things, whatever internal, external stability check, and in dynamic static condition, that is one thing we have to check, ultimate limit state of collapse. And second, we have to check the serviceability limit state also. Now, serviceability limit states means you have to check that deformations are within prescribed limit. And normally the deformation which you check is, if this is your retaining wall, this is your reinforced section, this is your normal thing, settlements. Depending on what type of soil is this, you calculate the settlement, total settlement, how much it will be. And then you define our code. If you see our bridge code, it's not very clearly defined. It says depending on importance and type of structure. Here also, if you see IRC and all, they define this maximum settlement 100. And sometimes you 1 in 300 or 1 in 500, you specify differential settlement also. So this is serviceability of limit state, what we use in our case. And as you must be knowing, whenever we follow limit state principle, there is something known as partial effective factor and overall safety factors. So when you apply partial safety factors, what you do? You increase the imposed loads by these factors. So if load is, let us say W, you will multiply it by FSM, whatever load factor for that. You will increase the applied loads and you will reduce or decrease the material. In case of material strength, you will divide it by this. So loads are increased by these factors and material strengths are decreased by these factors. And then when you check overall like stability, sliding and all those things, then you use overall safety factor, which depends on consequence of failure. If that failure happens, how catastrophic will the consequence, depending on these factors are given. So BS 8000 gives very big tables for in various conditions, which load, what factor is to be applied. So we must take from there partial safety factor and overall safety factor. So while analyzing For any particular mechanism, either external or internal, for materials and loads, we will use this factor, and after analysis, what factor is after you get safety factor, that will be compared with overall safety factor. This is basic philosophy which is followed in this. And this is simple diagram. Again, same thing. I will just repeat. This is selected backfill or reinforced fill from here, and its length is L. For length L, this is foundation soil. H, this height is taken as H from top of your leveling pad to top of your RE wall. Here, please understand what I am going to tell is only for horizontal fill. Sometime you may have inclined fill also. In that case, depending on this inclination B, you calculate another height H1 or whatever, that is taken as effective height. So in case it is inclined backfill, then there is a formula given. As per that, you must calculate H1, and that H1 will be used in place of H. But to make it simple, I have only taken a horizontal fill, which is the case in most of the cases. Then I have taken reinforcement as geogrid. If you take strips, again there will be some minor change. And this is retained fill. We also call it backfill. This is selected fill or reinforced fill. So here we normally use subscript R, like gamma R, CR, phi R. Here we use gamma phi, gamma B, CB, phi B. And for this we use F. Gamma F, CF, phi F, like that. So you must be familiar with this. L and H are these values. And then there is a surcharge loading. Total surcharge loading we give it by WS. It consists of live load loading and it consists of dead load loading, both. So using this concept, using these notations, we will do I will show you the equation. I have not done actual calculations. If you see RDSO G18, there are many 4 or 5 calculations done there. There are some mistakes here and there, but that you can correct with this background. Okay, up to here, if you got anything, please ask. Oh, we are already almost at 11 o'clock. Otherwise, we will take tea break and we will meet at 11:15. Any questions? Any doubt? No?
सर वो इंटरनल स्टेबिलिटी में थोड़ा सा इंटरनल स्टेबिलिटी जो था ना सर उसमें थोड़ा सा कंफ्यूजन था.
प्लीज टेल मी. आई विल गो बैक टू इंटरनल स्टेबिलिटी. इसमें टेंसाइल वाले में या दूसरे वाले में, एडहेरेंस वाले में?
यस सर, सेकंड वाले में.
नेक्स्ट वाले में, दिस वन, पुल आउट और एडहेरेंस वाले?
Yes sir.
I will explain again. See, what happens is, we want कि laterally कोई deformation नहीं हो, हमारा reinforcement इसको tie करके रखे, ये straight रहे, but it does not happen. There will always be some deformation in front. That's why normally you will see, जब आप RE wall construct करते हैं, even though we call it vertical, it is normally never vertical. It is given some pattern like this. So 5 degree, 6 degree, so that when it deforms, it becomes vertical. So there will always be some deformation. अब जब यहाँ movement हो गया, when this at the fulcrum, यहाँ 0 होगा movement, यहाँ maximum होगा, ये मान लीजिए थोड़ा सा आगे ऐसे move हो गई, it became like this. जो ये होगा, you know the principle of active earth pressure, जो पीछे wedge बनती है, this triangular, this shape also, there are different wedges. Only for the sake of simplicity, I am telling a triangular wedge बन जाता है. This yellow color wedge gets loosened. This yellow color thing has got loosened. ये लूज हो गया. इसमें अब जो यहाँ reinforcement और इसके बीच में जो टेंशन था वो नहीं रहा. So now this is active or potentially unstable zone. ये जो yellow वाला है.
क्लियर हुआ सर?
अभी क्लियर हो गया?
Yes sir, yes.
This is exerting a force T on this block. और इसमें ये फोर्स रेसिस्ट हो रहा है इस रेनफोर्समेंट और इनके बीच में adhesion या फ्रिक्शन से. So you calculate pull out resistance and the force T and their ratio is factor of safety. ठीक है?
Thank you sir.
Any other doubt? Anybody having? No? I hope my screen is visible to you.
Yes, sir.
Yes, sir.
So first we will calculate various loads. Of course, I have done this for railway loading. You can do for highway loading also. Approach remains same. There is not much of difference. So first we will calculate the dead load. I have developed again an Excel based spreadsheet on this, again using project work of two of my probationers last year. But as I told you, there are a lot of combinations: horizontal fill, inclined fill, then for geograde, then for strips. So that sort of furthermore generalization will take me some time. Maybe after some time I can put that also on Garrison website, but it is very simple. It's not very difficult thing to be done. So let us say now, first you can take load of rails per meter length of track, that is across your plane of projection or calculation per meter length. 2 rails, whatever is their weight, we can take that. Then we can take load of sleepers per meter length. Depending on sleeper spacing, you divide it by spacing. So whatever is weight of sleeper, you can convert into per meter length. And if you add this 1 and 2, so basically this is your rail. This is sleeper. And in this direction, perpendicular to this, you are taking, and finally what happens is this both load, it gets transmitted at the bottom of ballast through this width. So ballast section bottom width, normal single line section, I think it comes around 5.05 if I'm not wrong, but depending on your position and all, you can calculate how much it is. So this load per square meter area it will be. So 1 meter perpendicular to this and 1 meter in this direction. That is how units we must be careful, of course, you all know it. This is about dead load, and then you can take weight of ballast per square meter area. Total dead load will be 3 plus 4. So we call dead load as QD, dead load intensity basically it is per square meter area. Okay, correct it here. Meter area. And so this dead load intensity is QD. This nomenclature, please remember, we will use it later. Then live load, track loading intensity, whatever is there, we know, you all know from bridge rules, you can take it is 9.33 ton meter for 25 ton axle load. So if you are designing for 25 ton axle load, take this. This is per meter length. Then take dynamic augment or impact factor, which is given from bridge rule, and then live load at bottom of ballast QL will be equal to 1 plus 2 divided by ballast section bottom width, again whatever 5.5 meter or so, and this also correct per square meter area it will be. So we have calculated QD, you have calculated QL. If you are doing for highway, only thing is take highway loading and their standard. This is, since I am going as per G18 railway loading, so I have taken railway loads, not much of it. And first thing you have to do is you have to decide length of reinforcement, which will be length of your reinforced block, that what we will consider as rigid block in external stability analysis and block for analysis in internal stability. This is to be done as per, this is given in table 14 of BS 8006. It says it should be 0.7 H minimum or 3 meter. 0.7 H, if it is less than 3 meter, then you take minimum 3 meter or take 0.7 H to start with. So we will initially take it equal to 0.7 H or 3 meter, whatever is higher. Then after that we will calculate the coefficients of earth pressure coefficient of active earth pressure, which is given by Rankine formula. You all must be knowing Ka equal to 1 minus sin phi divided by 1 plus sin phi. So if you calculate it for reinforced fill, we call it KAR, and if you calculate it for retained fill or backfill, it will be KAB. So accordingly here, if you put phi R in both this, it will come for reinforced fill. If you put phi B, it will come for your retained fill or backfill. So KAR and KAB we will calculate. Then let us calculate the other vertical loads or vertical loads. So first will be weight of reinforced block. Reinforced block weight will denote by W. H is its height, L is length, and gamma R is density of reinforced fill. This will give me per meter length of track. So we will get gamma R. Gamma R also there can be two value. See this. The density of fill can have a maximum value and minimum value, which we check from shake table test in gamma max and gamma min, what we call. For any granular material, it can have two values. So gamma R also can have two values, gamma R maximum and gamma R minimum, depending on what is the maximum and minimum density. So that now the live load will be WS will be QL. QL was per meter, per square meter. So one was across the plane, along the plane, multiplied by L. So total live load per meter length of track. Now we are calculating everything. So it will be QL into L will be the live load, and similarly dead load will be QD into L. QD was dead load intensity per square meter, as we have calculated on previous things. So live load and dead load both we can calculate. Then horizontal loads. What will be the horizontal loads or forces? Earth pressure behind retained mass. So if this is my behind RE mass, if this is my RE fill with reinforcement, behind this it will be like this. It will be a triangle like this, and its value PH will be half KA, because this value is 0, this will be KA gamma B into H, if this is H. So total force area of this triangle, which will be half into KAB, because it is because of backfill, into gamma B into H square. And here gamma B also can have minimum and maximum value. So this PH also can have maximum and minimum two values. Now earth pressure due to live load surcharge. As you know, if this is my reinforced fill, and if some surcharge is acting here, let us say that surcharge value is Q, then earth pressure due to that will be a rectangle, and this value, its value will be Ka into Q. That is all. So by that same way, earth pressure due to live load surcharge PL will be KAB minus QL and multiplied by H, total force, if we want to calculate. Similarly, earth pressure due to dead load surcharge, P dead load will be KAB into Q dead load into H. So these are the horizontal forces. We have calculated vertical forces. Now your BS 8006 tells you that it gives you three load combinations which are given in table 12. Combination A, combination B, and combination C. What they are? Let us just see them. Combination A is, it says, consider maximum value of all loads, horizontal, vertical. So that's why that gamma B maximum, gamma R maximum you will use here in that formula. Second thing, it says that normally this combination, it generates the maximum reinforcement tension and foundation bearing pressure normally, but we have to check for all combinations, of course. And then it say this combination may also determine the reinforcement requirement to satisfy the pull-out resistance in internal stability, though pull-out resistance is usually governed by combination B. So it means it say this can be by combination A or B for pull-out resistance. So you have to use combination A or B. For internal check, you don't have to use C. That is what it means. Whereas for external check, we have to use all three. So now combination A, first in this table I put vertical load. So vertical load one is load the weight of reinforcement block, and that also because it says maximum. So W max. Then the component of surcharge WS and WD. And summation of all this will be summation RV. Similarly, horizontal load will be PL due to live load surcharge, the active earth pressure, PD, the active earth pressure due to dead load surcharge, and PH is active earth pressure due to backfill. We have seen in previous slide how much are their value, and here also when we are taking here gamma B, in this gamma B will be one of the input, so we must take gamma B maximum value because it says maximum value. So we must use the gamma B max rather. The summation of this will be summation RH, and then partial load factors, they are given in this table 12. So in this case, for all these, partial load factor is 1.5. Table 12 is given a different form, you have to read and understand it. I have summarized here 1.5. Now see the lever arm. Lever arm with respect to, see, this is my fascia and this is my reinforced fill. So all these forces, they were lever arm with respect to this point. So weight, lever arm weight will act in the center of this block. So lever arm will be L by 2 because this total is L. For this also lever arm will be L by 2. For this also L by 2. These two live load and dead load surcharge, because they are in a rectangular shape, so they will act as half the height. So lever arm with respect to this point will be H by 2, H by 2, and the earth pressure will act in a triangular. So here will be its resultant at H by 3. So you fill all these values here, multiplied by this, multiplied by lever arm, you will get moment. Sigma M. This is for combination 1. Then comes, combination A. Now come for combination B. Combination B, what it says, BS 8006, consider maximum overturning load. So whatever load is overturning means horizontal, consider that as maximum. So it means for gamma B and all, you have to use maximum value, and together with minimum self mass of structure and superimposed traffic load. So whatever is with gamma R, you consider their minimum value, and gamma B maximum value here. And this, it says, normally dictates reinforcement requirement for pull-out resistance. But in previous one, it has said A may also declare. So it means for pull-out check, we will use both combination A and B and check. And this is, it says, normally the worst case for sliding along the base. In any case, for external, we'll check all three, A, B, C, all three combination, and see that our wall is safe. For pull-out and other thing, we'll use only combination A and B. So again, same table. Here you see W vertical load, we have put minimum value. So you will take gamma R minimum in this case, because here it says minimum self load. Then WS, WD, all these values, PL, PD, they remain maximum only. Horizontal, we have to use gamma B max. Okay. Then partial load factor, again we will take from this table, and from there if you pick up for this, it will be 1. For this it is 0, for it is 1. Again for them it is 1.5. And lever arm of course will remain same, L by 2, L by 2, L by 2 for this, H by 2, H by 2 and H by 3, same like last. Again you find out sigma RV, sigma RH and this moments. Moments will be multiplication of 2 by 5 or 3 by 5 multiplied by 3 also has to be there. Just 1 minute. We have to multiply it by load factor also. Just 1 minute, let me correct. 8 by 4 and then multiplied by 5. So this has to, because partial load factor also we have to multiply. I forgot to write that. Here also we will write. Next one also same thing will be there. So this was for combination B. Again you will calculate all this sigma R, sigma V and sigma M. And then there is a combination C also, which is given in BS 8006. Combination C, it says consider only dead load without partial load factor. Only dead load, that too without partial load factor. And this, it says, it is used to determine foundation settlement and reinforcement tension for checking the serviceability limit state. So we will check this Means we will only take dead load, we will not apply partial factory shifter, and then use this load combination. Of course, external stability we will do, and we will also use it while calculating settlements. In internal stability check, we will not make use of combination C. So here again, this vertical load maximum, these are all again you can take, and here you see for whatever is your dead load, factor of safety or surcharge load 0, and for live load wherever it is there we have put partial load factor 0 because we don't have to take live load, and these are lever arm. Again you multiply them, get this value and get sigma RV, sigma RH and sigma M. So 3 combinations you have to calculate sigma RV, sigma RH and sigma, and that's why the easiest way is to make a spreadsheet. There you just value automatically everything comes. That is what we have done. Okay, here everybody is comfortable how these 3 combinations and how loads are to be calculated and moments.
Yes, clear, sir.
Right. Now for all these 3, yes,
आपने पूछा, आपको याद आ रही है इसके लिए?
Now for all these 3 combinations, now what you have to do is, for all 3, one by one, you must first calculate the location of resultant force from toe of the wall. If this is toe of your wall, this point, and you have got some vertical forces, you have got some horizontal forces. So where is the resultant striking here? This distance D. From that will be moment divided by vertical. Sigma M divided by sigma RV, and eccentricity E will be L by 2 minus D. If from toe, center's distance is L by 2 and D is the resultant force location, so this will be eccentricity, and vertical stress as base of wall sigma V will be sigma RV divided by L minus 2E, that Mayer-Hoff principle what I told you. With that you will calculate sigma V. So now we will check whatever our 4 checks are there after having done. So external stability check again for all 3 combinations. First let us check against forward sliding. So forward sliding, your resisting force is vertical force sigma RV divided by tan theta of retained fill, tan phi dash R in effective condition. This is that partial factor of safety FMS, which as per again BS 8006 we have to take 1 for forward sliding. So we have to divide it because this is my resistance or property, so divide it, and this is from phi component and this is from C component friction. So C dash multiplied by L is length of your total block, again FMS, of course FMS value is 1. So this will be the resisting force from C component of soil, from phi component of soil, and factor of safety for this against forward sliding will be resisting force divided by disturbing force. Disturbing force is summation RH. Disturbing force is summation RH, and this is resisting force. This is overall factor of safety, and overall factor of safety as per this code for this case we should get minimum 1.2. So this is check against forward sliding, very simple. Then check for bearing capacity or tilting failure at the base of wall. So for that, first we will calculate net ultimate bearing capacity. This formula is given in our IS code also. There are 3 components, NC, NQ and N gamma. NQ we neglect in this case. We only take NC and N gamma. So this formula is given there. Net ultimate bearing capacity formula in IS code, C into NC. NC is bearing capacity factor. 0.5 gamma R multiplied by L minus 2E, that is the area in which it is working, and N gamma is again bearing capacity factor. So this value C, NC and N gamma is basically for foundation soil, because we are talking about bearing capacity of foundation soil. So they will be basically F value, foundation value, CF, C dash F rather, and for foundation material whatever is phi value corresponding to phi, NC, NQ, N gamma values are given in IS 6403, this equation as well as this. So from there you find NC and NQ. So this is my net ultimate bearing capacity. Now, as you must be knowing, when you have to calculate safe bearing capacity, you have to first divide net ultimate by your factor of safety, partial factor of safety, which is 1.35 in this case as per the code, and then you can add the whatever is overburden, whatever is, in foundation cases also we do like this. If you remember, if this is my foundation and if this is DF, then for calculating safe bearing capacity, you do QNF divided by factor plus gamma time DF, because you are backfilling this area. So here the soil which you are filling is reinforced soil, and DM is embedment depth. In this case, this is my embedment depth. This much it is embedded. My wall is embedded here. So this is embedment depth, DM. So gamma R plus DM, and embedment depth, it is not given in BS 8006. Again, as I said, these are construction aspects. So FSWA gives it. It says it can be taken as H by 20. Same is taken in IRC also, subject to minimum of 0.45 meter for horizontal fill. If your fill here is like this, then there is different formula, but we are taking horizontal. For horizontal, it can be H by 20, subject to minimum of 0.45 meter. So with that, we will take this DM, and you will calculate safe bearing capacity. So net ultimate bearing capacity and safe bearing capacity here also. Let me get so that there is no fusion. Yeah. Now come to next. I hope we have seen dead load, live load, vertical load, A, B, C, then this we forgot. The vertical stress at base of wall, that is sigma V, we have already calculated here. This should be less than QS, your safe bearing capacity. Whatever QS you are calculating, it must be less than safe bearing capacity. Okay, so this is check for bearing capacity. Next is check against overturning at toe of wall. Very simple. You calculate positive moments from those tables due to vertical load. You calculate negative moments due to horizontal load. So first column in that will give you positive moment. Second column after serial number in those tables. Third column will give you negative moments, and your factor of safety will be positive moments divided by negative moment. And here overall factor of safety is also given 1 as per code. So your positive moment should be less than your negative moment. So this is check against overturning at toe of wall, the third check. And fourth check is check for global stability, that is slope failure. So for this, you consider reinforced fill as a rigid body. In every slope stability program, there is a provision to give something as rigid body, something as soil. So use that, give it as a rigid body, and then do slope stability analysis using a suitable software, that is preferable method, as I told you previously also. Or roughly if you want to do, then there is a graphical method which tells how to locate center of most critical circle, what will be the radius of most critical circle. So there what you will do is you will take this, then you will take this as rigid boundary. Here you will get location of this with reference to toe of this by getting XY coordinate. There are method given there, and then radius. So then you will draw a circle like this. Then in this circle like this, then you will make slices, then each slice weight, and there is a calculation method which I feel is more cumbersome. You must use software. So this approach is given by Felenius in 1953 for cohesionless soil, and it was extended by Jumikis in 1962 for C5 soil. So we have to use the Felenius approach extended by Jumikis. And requirement is factor of safety for critical slip surface should be more than 1.4. Now this code does not say any factor of safety. It says as per your whatever is your country standard. Our earthwork guidelines in RDSO, if you see the specification and guidelines which we had issued last year September, there it says that for banks up to 4 meter height, above 4 meter height, long-term factor of safety should be 1.4. And for banks less than 4 meter height, it it has to be 1.6. So from there we have taken 1.4. Normally it will be more than 4 meter. So we have taken 1.4. That is what factor of safety for slip circle. And after having done all these 4 checks, let us say any of these checks fail. Then what does it mean? It means the stabilizing forces being provided, which is mostly the weight of your retained fill and associated parameters, is less than your disturbing forces. So if any of these checks fail, 4 checks, then what you have to do is you have to increase the L, means increase the length of your reinforced fill, which we have taken 0.7 times H or 3 meter minimum. Increase it and increase in such a way till you achieve required factor of safety in all these 4 cases. And this will confirm your external stability check. Clear? Any doubt in this external stability check to anybody? Any question, any problem, any doubt, anything?
No, sir.
Clear, sir.
Clear. Okay. Very simple calculations. Only thing is there are repetitive calculations, values are used from one place to another. So that's why what I prefer is whenever I do this calculation, I made some spreadsheets. And in fact, when we go internal stability check, further many fields interrelated here to here, make Excel sheets and give relative reference of the cells. Automatically values will be picked and you can do it very fast. That was for static condition, external stability check with static condition. Now we will check for earthquake condition with dynamic condition. Now dynamic condition, we follow the approach given by FHWA code. So first, before that, some coefficients that we will use as per IAS 1893. Now there is a clause 6.4.2 of IAS 1893 part 1 2016, and it says the design horizontal seismic coefficient, means it is basically ground acceleration at that place. Our wall acceleration will be different from this. This is ground acceleration AH. Its value is given by 3 things. One is Z by 2 multiplied by SA by G divided by R by I. So we need Z, we need SA by G, and we need R by I. So what they are and how do we take? Z is given as zone factor. It is given in table 3 of IS code part 1 2016. So from there, and these are the values. For zone 2, more severe is the zone, more is this value naturally. For zone 2 it is 0.1, for zone 3 0.16, for zone 4 0.24, and for zone 5 it is 0.36. So you take these values depending on which zone you are located. First Z we have taken. I is called importance factor, means how important is your structure. If it fails, what are the consequences, how catastrophic it is given in table 8 of IS 1893. There it is taken as 1.5, which is maximum value. So we take it that it is very important. We don't tolerate any failure of this. This is 1.5 is maximum value there. Then R is response reduction factor, which is given in table 9 of IS 1893. And there are a lot of values are given. From there we take value as 2.5 for RE wall. So now left over is SA by G. SA by G is called as, if you read this code, many of you are all from design, so you must be knowing. It is called average response acceleration coefficient, which is given in clause 6.4.3. Actually, it depends on, if you see the chart in the IS code, it is something like this. This is SA by G and this is time period. How long your earthquake lasts, 1 second, 2 second, 3rd second. And it chart is something like this, very sharply trisé, then some length horizontal, and then it comes like this, something like this. So we have taken the maximum value here also. So 2.5, this value is 2.5 SA by G. So all these coefficients we have taken from IS code, and then as per FHWA, these codes we have used in FHWA, it says the maximum horizontal acceleration in wall. Here AH is for ground. Let us say at this place where I am in Pune, if my ground accelerates with AH, my wall will accelerate with some other value am, and this formula is given am equal to 1.45 minus a multiplied by a, and a is maximum ground acceleration coefficient. A is, for that, what is maximum ground acceleration coefficient? So you can take ah, maximum value, and then you calculate am. For zone 3, I think it comes 1.2 or something, if I am not wrong. Okay, I hope up to here it is okay. First part, when we do with dynamic loading, this will be used in internal stability check also with dynamic loading. Basically, you calculate am, what will be the horizontal acceleration coefficient which will be used for the wall. This is common. ठीक है? आया समझ में या नहीं आया?
Yes, sir.
Sir, FHWA, what is this?
Federal Highway Authority, it is like CPWD of United States of America. It is like CPWD of USA. Okay. Federal Highway Authority. It is the regulatory authority in US for all highway related works.
सर जो सीस्मिक के कारण जो हॉरिजॉन्टल लोडिंग आएगा उसका पॉइंट ऑफ एक्शन कहाँ पे रहेगा सर आर्य वॉल पे?
अभी बताएं, अभी अगले बताएं कहाँ कितना
that A is AH, no? Here.
Pardon?
That in formula AM equal to 1.45 minus A into A. That A is AH.
A is AH. A we will take equal to AH because for our area we have AH, so we will take A equal to AH and calculate AM. Okay.
Right, sir. Thank you.
Now, that's why I have written here also. Take AM equal to AH for horizontal backfill. If your backfill is inclined, there is a very complicated formula, alpha, beta, gamma. There is a Japanese formula which is used there. But for horizontal backfill, you can take AM equal to AH. For inclined backfill, there is a very, very complicated where theta, beta, gamma, delta, so many things they come into picture. We will, because of this horizontal acceleration, because of earthquake, we will calculate horizontal or seismic inertia force per meter length of wall, means perpendicular to our plane of working. There will be, that is called PIR. This is inertia force, means if this is my fascia and this is my reinforced fill, because of this, its weight, inertia of this, whatever horizontal force extra will come, this is given, again it is given in FSWA code, it is 0.5 AM gamma R H square, PIR. Seismic thrust per meter length of wall exerted by backfill. Because of this backfill, this was because of weight of this effect of earthquake, and because of backfill, whatever is the action, that is called PAE. This formula, again it is from FSWA, 0.375 AM here gamma B by H square. Okay. So these are the forces. We'll see their point of how much. Now, again the same thing we will analyze. Same table we will analyze. This time we'll take W max, WS, WD. They are acting at L by 2, L by 2, L by 2. And here, if you see in dynamic condition combination C, you take partial factor of safety H1. So you don't apply any factor of safety here. So multiply by this. Now, there are two things. Number one, it says the whatever is live load PL, you must take 50% of that. So you have multiplied, previously it was PL by 0.5 PL, and live load is acting at H by 2. Then PD and PH, they are also acting at the same place. These two are extra because of dynamic thing. One change is here, at half of live load we have to take, and these are, so PIR is this, PIR, and PIR it says it acts at 0.6 times H from the bottom. That is what it said in the code, that you take acting at 0.6 times H. As somebody was asking, this is the lever arm for PIR, and it said take half of the seismic thrust exerted by backfill, that is PAE. So you take 0.5 times PAE, and this acts at the middle of the wall. So you take at h by 2. Okay, somebody has just asked this question. So this is the lever arm which is given in the code, the 0.6 and here 0.5 or h by 2. So with this lever arm, now again you can calculate positive moment, negative moment, all the moments, and again sigma RV, sigma RH, sigma M. Clear? I hope now that question is answered. ये दोनों force, दोनों component कहाँ लगेंगे? There will be two components. Both will be acting at different locations. All right?
Yes, sir.
Right, sir.
Now, again using these dynamic values, see, these dynamic values, what we have come here, sigma RV, sigma RH and sigma M, you calculate, check it for forward sliding, as we have done previously, check it for bearing capacity at the base of the wall, check it for overturning at the toe of wall, and check it for global stability, that is slope. Again, same formula is same previously, only values will change, sigma RV and sigma RH and your sigma M moment and positive negative moment. And again, if any of the checks fail, only solution is increase the L till you reach the required factor of safety. So first you have fixed L at 0.7H, then check whether that L is sufficient for static external stability check. You may have to revise it. Then check whether that revised H is safe for dynamic condition of external stability. You may have to revise it. Now this will be your revised L value if you need to revise it. So with this, now external stability check is over for both static as well as dynamic condition. Okay. Here, up to here, no question, no doubt. We can go to internal stability check now.
Right, sir.
Right. So now let us check internal stability first for static condition, then for dynamic condition. So for internal stability check, there are actually two approaches. One approach, which is very common, is called tie-back wedge method, and this is used for geosynthetic reinforcement, or there sometimes also they call it extensible reinforcement. Some strain is allowed there. Tie-back wedge method. So that's why we will use this only. There is another method which is coherent gravity method, which is used, word used is inextensible, but it is used for steel reinforcements. As I told you, nowadays we are not using steel reinforcement, so I am not going to discuss this. I am going to discuss only tie-back wedge method. Even otherwise also, I will tell you just after this, there is not much of difference between the two. I will tell you what is the basic difference. Otherwise, there is not much of difference between the two. So we will see by tie-back wedge method. So we will use tie-back wedge method for internal stability. So here, if you see, this is my fascia, this height is H, this surcharge is WS, which consists of WD and WL and WD, dead load and live load surcharge. Then this is my reinforced fill. Its property is phi gamma R and phi dash R. This is my backfill, retained fill. Its property is gamma B and phi dash B. This is my reinforcement layers, which are geogrid. And at any depth HI, HI is the depth where this geogrid layer is situated. The tension in this geogrid layer is Ti, and Vi is the effective spacing of this geogrid. Is for effective spacing, what you do, whatever is spacing on top, half of that, whatever is spacing on bottom, half of that, combine that. Vi is known as effective spacing. L is my length of reinforced zone or reinforced block, and behind this here, whatever is my earth pressure is acting, one is active earth pressure due to backfill, that will be KAB times gamma B into H, and this is due to surcharge because this is rectangular, so this will be KAB times WS. So at any point, if I want to know the active earth pressure, this will be KAB times, at this level, if I want to know HI, KB gamma B HI plus WS. Simple equations of earth pressure and gravity and all, nothing different. Now in only difference in tie-back wedge and all, as I told you, in tie-back wedge method, it assumes that there will be some movement of the wall here, and because of that, a wedge will be created, which is like your active earth pressure zone moving out, and this area will only provide destabilizing thing. This will not contribute. this area will resist the whatever forces. So this shape of this wedge is assumed to be triangular, and it makes an angle with vertical as 45 minus phi r by 2, like active earth pressure wedge, if you remember. Or if you take from horizontal, this angle will become 45 plus phi r by 2. So this is what is assumed in active zone in Tyvek wedge method. The only difference between this and coherent gravity is, in coherent gravity you assume this wedge to be type of rectangular for some length, and then it becomes triangular. Normally I think up to 0.6 it is rectangular and 0.4 of the height. This is the only difference between Tyvek wedge and coherent gravity, and reason for that is people with various experiments and research, they have found that normally, depending on type of reinforcement, this sort of active wedge is formed. So this is the only difference. So this is my configuration diagram for internal stability check. Okay, this is clear to everybody? What are various forces and all?
Clear, sir.
Right.
Clear, sir.
So now, okay. Now we will check for tensile force. As I told you, in internal stability there are two checks. Tensile force, it should not rupture and it should not get pulled out. So tensile force check. Now the tensile force in the reinforcement is taken due to self weight of reinforced fill, basically sigma V. Sigma V times Ka, that is what will be horizontal stress at that location, and if I multiply it by Vi spacing, then this will become horizontal force, as we have seen earlier. So for calculating sigma V, we will take self weight of reinforced fill, then we will take surcharge load also for load case A and B. As I told you, for combination C, we only do settlement and external stability. Internal stability, we use only load case A and B. But when you are using load case A, you will use total surcharge, and when you use load case B, you will only use dead load surcharge, because it is given there in load combination that for live load its factor of safety will be 0. The partial factor we will not take, it will be 0. So that's why this we must be careful that how we must take WS value for both the cases. Then formula for simple sigma Vi we will calculate at that level considering these loads. KAR we will multiply. KAR is coefficient of active earth pressure coefficient for my retained fill, and Vi is effective spacing. So this is the tensile force per meter width in any reinforcement layer which is at depth Hi. This is the tensile force. KAR is active earth pressure coefficient for reinforcement. Sigma Vi is vertical stress at depth Hi. Vi is effective vertical spacing. I already told you, because normally your reinforcement spacing is not constant throughout, because your forces are not constant. So that's why one value will not be there. You take half of the value above and half below and then add them for every layer. And sigma Vi, there is a formula given there. This is based on simple earth pressure calculations, but rather than drawing this is given as P divided by 1 minus Q by P. P is gamma R into Hi plus Ws. Here, let me put a bracket to avoid any confusion. R to Hi this value P is gamma R into Hi plus Ws, and Q is given KAB for backfill multiplied by gamma B into Hi plus 3 times Ws into Hi by L square. This after all formula combined they are derived, so we can directly use this formula. So sigma Vi will come by this formula. Vi we will see from geometry. KAR we can calculate. KAB they are all material property or dimension. So for every reinforcement layer, this Hi will be different, depth from top, first reinforcement, second. We will calculate this tensile force for every layer. Okay. And as I told you, normally the reinforcement spacing, that is the vertical spacing between reinforcement, this in top 2/3 height of wall is kept more. In top it is more. So that is normally 0.7 to 0.75 meters. So maybe initially when you put your reinforcement. You can try with 0.7 or 0.75 in top 2/3 height, and bottom 1/3 height you keep it less, because here forces are more, and normally you keep about 0.5 meter. So normally what you do is with 0.7 and 0.5 you arrange your reinforcement and then check it. Then check your reinforcement that your tensile stress is not coming more. If it is coming more, either you increase the spacing, but don't make it too close, less than 0.4 or something, and or you increase the length of your reinforcement block. Simple. Now, for load case A, again as per BS that thing, we use partial factor of 1.5 with gamma R, gamma B and WS. Wherever we use this gamma R, gamma B and WS in previous formula, use this partial safety factors, and for load case B, this value is 1. So you don't have to really use any partial factors. Then using this, calculate TI, means reinforcement is A's share of reinforcement for both load cases, means both A and B, both load case, every layer. That's why I said there is a lot of calculation, but it's repetitive, so always better to make a spreadsheet so that things automatically get, once you change one parameter, everything gets recalculated automatically. And then you must calculate factor of safety against tensile failure. In that layer, TI is the tension, and TAL will be, sorry, I have put it wrong, L by TI. AL divided by TI. Allowable load divided by actual load. So that will always be factor of safety. So TAL by TI. TAL is long-term allowable tensile strength of reinforcement. This is my strength, this is actual load. And how this is calculated? Long-term allowable tensile strength, ultimate tensile strength is given. Like I have shown you those strips, 50, 80, 90, they are all ultimate tensile strength. Similarly for geogrid also, it is given by manufacturers. This is the main parameter. Then you divide them by addition of 3 reduction factors. What are those reduction factors? First RF. So T ultimate is ultimate tensile strength of reinforcement. RF CR is known as reduction factor for creep. Creep will happen in the future. That time also it must be safe. So reduction of factor of creep, code says it should not be more than or equal to 1.5. Cannot be less than 1.5. And this value will be given to you by manufacturer. What is the actual value? Otherwise, we have to do the creep test, which is a long test, very difficult. But manufacturer gives you. He is supposed to specify you what is the creep reduction factor. Next reduction factor. Again, there was some mistake. Just me correct. Yeah. Next reduction factor is called reduction factor for installation damage. Means during installation you will handle it, roller will run over that, so there will be some damage. So this value is for synthetic strips you use 1.5 or more than that, or for geogrid, either it can be grid, geogrid or synthetic strip. In geosynthetics, for them it is minimum 1.2, and this is to be determined by doing installation damage test. There is a ASTM test, or manufacturer might give, because this will depend on type of machinery which you are using, the type of soil which you are using, and type of reinforcement. So either same type of machinery, soil and reinforcement results are available with you. Otherwise what you do is, basically it is very simple test. Let us say this is your geogrid. You do a tensile test and find out its ultimate tensile strength. Then you lay this geogrid in your site, whatever soil you are going to use with rolling and all, you put it there. Then you excavate it and take it out, exhume it, take out this geogrid, and again do an UTS test. Let us say this time UTS value is UTS 1. Then this damage factor is UTS 1 divided by UTS. Means how much loss, sorry, UTS by UTS 1, whichever it is higher value. So how much loss in tensile strength due to installation damage. That is called reduction factor for installation damage. Normally our people, they take 1.2, 1.3 and say okay. But better we can do a test. This is not very difficult to be done. And next reduction factor is reduction factor for durability. Today what I have put, it may not remain durable same in life. There may be some deterioration because of various vector. So durability also for strips, it is minimum 1.15. For geogrid, it is 1.3. And this also is to be given to you by manufacturer, because there is a standard ASTM code for checking this, or ISO code for checking this. And as per that, he will give you this value. So now if we go to previous slide, using these factor of safety, this, whatever is your ultimate tensile strength, you will add these three of factor of safety, divide. And typically if you see their value, it can come up to 3 or so, 3, 4 between them. So it means your long-term allowable strength will be quite less than ultimate tensile strength. Please be aware of this. We will not, should not take ultimate tensile strength, otherwise we will be making a very big error. That is what should be clear. And then the factor of safety, which we calculated for tension, for both load cases, that is case A and B, for all reinforcement layers, it should not be less than 1.1, which is given in table 9. So this is my tensile rupture test of the strip. First I calculate tension in every strip, and then I calculate the allowable tensile load, allowable tensile strength, allowable tensile strength divided by tension. My factor of safety should not be less than 1.1 for static case we are talking. If it is less, then either you have to decrease the spacing or you have to increase the length of reinforced block. Clear? I hope this is okay. Simple checks, not very difficult. Right. Now next, check, we are still in static check for internal stability. Next is check for pull out or wedge failure. So as I told you, we use the tie back wedge method where wedges will be made. Now here we check for different wedges, and which is, let us say we check any wedge at height h. Then this wedge at angle beta, we saw what is the beta. Now there may be another wedge here, there may be another wedge here, like that. So normally we take wedge at every this reinforcement location, and we have to check it for this. So when there, so that's why I said there are a lot of repetitive calculation. You need a spreadsheet, otherwise doing manually becomes difficult. So let us say if this wedge is formed, then this will be your destabilizing wedge. Self weight of the fill plus it will put some, it will try to go like this, and the anchorage by these length, whatever is cutting, because this reinforcement will not come into picture for this wedge, they are not. So anchorage given by this will give you the stabilizer's force. That is what is the approach for calculation. So here, first we will find out the mobilized force, which is the wedge, how much force it is giving. So for any wedge which is starting at depth h, the mobilized tensile force is calculated as under the formula is given in the code. It is equal to h into 10 beta into gamma r by h plus 2 times ws divided by 2 times 10 phi r plus beta. Beta is angle of inclination of the wedge with the vertical. And this, as I told you, always 45 minus phi r by 2 with vertical. Phi r is effective angle of internal friction for reinforced fill, and ws for load case A, it will be QD plus QL, and for load case B, we will not take live load, we will only take dead load. So using this, for both combinations, we can find how much is the mobilized force due to wedge. And this wedge will be, we have to consider 1, 2, 3, 4 wedge at every reinforcement level. So calculate T for various wedges at every 1.5 to 1 meter depth, or at every reinforcement depth, whatever you want. And for both the load case, for load case A and B, we have to have separate tables. Again, Excel makes it very easy. And to calculate resisting force. So let us say if this is the wedge, okay, and this wedge, if this wedge is formed and it is cutting this, whatever reinforcement is cut, that their adherence here, this length only will be useful. This length has become loosened. So this length is called LIP. Whatever length which is still mobilizing the tension, and this is total length. Wedge angle is of course 45 minus phi r by 2. Now for resisting force, the anchorage force in reinforcement at depth h, in any reinforcement which is at depth h, the anchorage force in that is given by this formula, TAI is equal to LIP 2 times alpha P tan phi dash R multiplied by gamma R into H plus WS divided by factor of safety. And what are these things? LIP, the length of reinforcement beyond failure plane, as I have shown you, which is giving you anchorage. Alpha P is interaction. It is basically coefficient of interaction of reinforcement with soil. Friction, basically it is friction. So this value, either this value is taken as 0.921 for granular fields because they will be more interlocking there, and should be less than or equal to 9 for cohesive fields. But this is determined pull-out test. Either you can do actual pull-out test at site. Sorry, there is again a spelling mistake. So we have to do a pull-out test at site, either actually or manufacturer gives you. So normally manufacturer gives you for different type of soils. So this is how your coefficient. WS will be QD plus QL for load case A and will be equal to only QD for load case B, and factor of safety here overall we take as 2 as per code. So by using this formula, first you have found out the mobilizing force, this is resisting force, and in some reinforcement, if your mobilized force, anchorage force is coming more than allowable force, then you will not take more than allowable, you will take equal to allowable, because your reinforcement cannot take more than allowable load. So there this check also has to be done. And then you calculate this TAI for all the reinforcement layers which are beyond the failure plane, means still in anchorage. Sum them up, you will get the resisting force and do it for both load cases. So for every layer you calculate this force TAI, take summation of TAI. So the total resisting force, summation of TAI, this should be more than total mobilized force T for both load cases. This is what your pull-out or anchorage test. This was for static condition. And dynamic loading, there is little bit of difference, not much. So printing mistakes which I have made. Okay. Now for dynamic loading, the seismic force causes an inertial force Pi, which acts horizontally in addition to the existing static force T. So whatever tension was acting initially in any reinforcement layer, there will be an additional inertial force because of dynamic loading. That is what is the concept. And how we calculate is this very simple method. First, this is the formula for Pi is equal to AM. AM same as what we have done for external stability check, same value of AM, and WA. WA is weight of the active zone, the wedge, which has become unstable. So this will be equal to self weight of the reinforced fill plus surcharge load, taking only dead load. WS equal to QD. Live load you will not take. And AM we have already calculated, maximum wall acceleration coefficient previously. And it is assumed that the tensile force line does not change during seismic condition. So it will still act in your reinforcement, you will only add. And the dynamic increment, whatever is dynamic increment, this Pi acts on the wedge of the weight of the full wedge. It will act on the full wedge, that is assumed. And now with this, very simple, we will do the tensile force check in the reinforcement. So for this, the dynamic increment induced by the tensile force Pi in different reinforcement layers. Previously this TID dynamic, this load, now it was TI previously, now it is TID force because including dynamic. So this is distributed in this ratio. Extra dynamic load is TID is Pi. Pi we have seen in previous slide, multiplied by LIP divided by total LIP. If you remember, this was the wedge, this was LIP. So for any layer, if this is LIP, all layers, whatever is total LIP, if you divide that in this proportion, it is distributed in each layer. So now we know in each layer how much extra load will be there, and you will calculate total tensile force. TID dynamic, and this was static, which we have calculated previously. And so calculate this for each layer, each reinforcement layer for both A and B. And factor of safety, here also I have made a mistake. This will be this TALD divided by T total. What is TALD? I will just tell you. So your factor of safety here will be allowable long-term load under dynamic condition. Previously we have seen under static condition, ultimate divided by those factor of safety and divided whatever is your total force, and when this value will be T ultimate divided by this. Here the creep reduction factor you don't take into account while calculating under dynamic condition, because this is a very short-term load in dynamic, and that time creep will not be effective, and therefore TALD means long-term allowable tensile strength of reinforcement for dynamic condition. Previously, if you remember, in static condition there was RFCR, creep resistance. That is not taken into account. You take only installation damage and durability. And then again same, that factor of safety for all the reinforcement layers, it should not be less than 1.10. Here given is 1.10. 1.10 is the factor of safety given in IS code. Same for pull-out failure. First you calculate mobilized force for any wedge. This is in dynamic condition. Same formula as was in static condition. Only thing is here WS value you will only take QD, whereas in previous one it was QL plus QD. For one combination, another only QD. So you will calculate the force. Same way like previous, calculate tension, the value of T, this T, the mobilized force for every wedge, and then resisting force also TA. Now this is TAID. So here only difference is QP. The alpha P has become alpha PP. That's all. So the interaction factor, it is 0.8 times than in static condition. You have to reduce less, and factor of safety will be same too. So again calculate anchorage force in each reinforcement, then calculate total and calculate TID for total. So total in dynamic condition, whatever is mobilized resisting force, it should be more than mobilizing force. So this is dynamic stability check. Any question in this? I think we are running little bit behind time. Quickly, just another one or two more slides, we'll wind it off. Any question in this? Simple calculations, only some value change, something you add, something you deduct. That's all. Same like static condition. Clear? Okay, I hope. Can we go to next slide?
Yes, sir.
Okay. This is the last check. Check for serviceability, and we check for vertical settlement. Again, very simple calculation. You calculate settlement only for dead load, because this is given in combination C of 8006. So for their concept is, if this is your subsoil, it may consist of 2-3 layers. So at center of every layer, first you calculate the initial vertical pressure, what you call P0. So like if we take center of this layer, it will be weight of this. If I take center of weight layer, this weight. So this is known as initial vertical pressure at center of all substrata layers in foundation, basically due to dead load of substrata. And then when you construct embankment here, what will be the increase because of this embankment load? What will be the increase? Delta P0 or delta P. So P0 was initially, and it will be increased by delta P. So calculate increase in this pressure delta P due to construction of embankment, and for that there are various methods like Newman's chart, but most common method which is used for embankment method is an Osterberg charts, which gives you some influence value for embankment loading. There you have to give this dimension, this center and height. Then very simple, this is an Osterberg method. I have put in that spreadsheet also. So with that you can calculate delta P, and then you find out pre-consolidation pressure, especially clay soil for substrata. This is done from consolidation test or audiometer test, PC value, and then it is very, very simple. Once you calculate this, settlement of any layer up to PC. If your total force is less than PC, then let us say this is your P0 plus delta P load, and somewhere here is PC. Then there will be one settlement up to PC, one will be, sorry, this is your P0, this is your PC, and this is your P0 plus delta P. So one settlement here to here, another here to here. But if this P0 happens to be on this side, then there will be only second settlement. This is what is meant by this. So settlement from up to PC is given by this formula, S1 equal to delta E divided by 1 plus E0 multiplied by H. H is height of the layer, the compressible soil layer. E0 is its initial void ratio, which we find out in consolidation test, and delta is change in void ratio due to construction of embankment. That also you can find out from your consolidation. And then settlement of layer from PC to P0 plus delta P is given by this formula. Again, all H, E0. CC is compression index, which you find out from consolidation test. Then you sum up S1 and S2 for all the substrata layers. You get total S, and then you multiply S by a factor lambda, which is given in IS 8009. It depends on type of soil in substrata. These are the lambda value: very sensitive clay, normally consolidated clay, over consolidated, heavily consolidated. So depending on what type of soil is, you take value of lambda, multiplied lambda to S, that will be your actual settlement, and this should be within permissible limit. As I told you, in IRC they take it 100 mm. Our case, depending on type of bridge and its span, you take it. So this is serviceability check. That's all. That is end of it. Sorry, we are late. If you have got any question, please ask quickly. Otherwise, we will hand over the baton to next faculty.
सर किस साइड तक आरी वाल बनाना चाहिए सर?
किस साइड पे? किसी भी साइड पे बना सकते हैं.
हाइट सर.
हाइट तक. See, as I told you, as such there is no restriction. Theoretically, in India we have constructed up to 80 meter also, but in railway we are a bit apprehensive. So I will say 9-10 meter तक तो आसानी से बना ही लीजिए. If you are constructing more than 9 or 10 meter, then be very careful, do detailed calculation and take more care. But up to 9 meter or 10 meter should not have much of fear.
नहीं, विड्थ रेशियो, अगर जो विड्थ हाइट रेशियो सर जो है,
हाँ,
विड्थ हाइट रेशियो जो है 1.1 से ज्यादा आ रही है सर जो है, तो उस केस में क्या बेस में?
देखिए ऐसा है ना, यदि आपके दोनों आरी वाल के दो एंड हैं, you are basically trying to tell there are both side आरी वाल and that width of bank available is less, isn't it? वो अपने आप आपके इंटरनल स्टेबिलिटी चेक में वेज बहुत छोटा हो जाएगा. Your force will become very high. So that will tell you कि ये नहीं सेफ हो रहा है. डिजाइन में आएगा ही नहीं. The design will automatically tell you कि ये नहीं हो पाएगा. Okay. आपका एक का इन्फ्लुएंस जोन दूसरे के इन्फ्लुएंस जोन से 0.7 and 0.7, as I told you, 0.7 H is your minimum. So 0.7 and 0.7, 1.4 H तो minimum आपको वैसे ही चाहिए दोनों के बीच में, right? 1.4 H is minimum. So you उसको increase कर लीजिए, 1.8 कर लीजिए, 2 कर लीजिए, maybe like that roughly you can take some factor. But for that also there are methods. ऐसा नहीं है कि technically it is insurmountable. Technically it is possible to do. But रेलवे में अभी हमारा कॉन्फिडेंस नहीं है, तो मान लीजिए 9-10 मीटर से ऊपर नहीं जाएंगे, 9 to 10 मीटर, not more than that.
सर कंस्ट्रक्शन जॉइंट्स कितना लेंथ तक जा सकते हैं हम ए वॉल से?
Construction joint means I could not get. Can you please repeat? I did not get.
No, maximum length of the wall. Any length we can build.
Yeah. Any length theoretically. See, I did not cover many things. Sometime your wall, some part of wall will act on the ground, some part of wall will be on the pile cap, isn't it? आपका अबटमेंट के बिल्कुल पीछे जब आएंगे, so there then you have to take different coefficient and checking. That method is also there, and we must always start preferably from the abutment and then go away. Normally हम दूसरी तरफ से start करके abutment के पास में आते हैं, उसमें problem आती है. Start from abutment and then go away, and we can go to any length. Length is not a constant.
Okay, like in normal walls we will provide joints, construction joints. It is not required.
Here, see what happens is already joint is built in between your panels, and if you go further into construction, I have not gone, वहाँ एक EDPM pad लगता है. It is an elastic pad which takes care of your temperature expansion and contraction. EDPM pad लगता है उनके हर joint के बीच में. That takes care of sealing.
And it is valid also for waterway bridges. We can build.
No. At here I will say no, because if water is there, then it creates a lot of problem. Your friction may not mobilize and all. So waterway bridges, I will probably say at this stage, no, not for waterway bridges. Not for waterway bridges.
Okay, we can build for lined canals and all, not for natural.
Basically, see, water should not go and change the properties of your reinforced fill. That is what my concern is there. क्योंकि उसमें यदि saturation बहुत ज़्यादा हो गया, पानी चला गया, तो all my reinforcement, this interaction and all those actions, they will be lost.
Right, sir. Thank you.
Any other questions? I think in any case we have got interaction section after this. If you have any question, you can ask there also, isn't it? Because we are late. I got a bit late, so we can hand over to next faculty. You can. Any questions?
Excel sheet नहीं share किया sir?
Pardon?
Excel sheet नहीं share किया?
Excel sheet जैसे मैंने आपको बताया ना, actually Excel sheet में क्या, there are lot of combinations. So I am developing it. I have for one combination which I have taught you, I have done it 90%. मैं 1-2 महीने में उसको ready कर दूंगा and then I will post it on the Irison website after taking of that horizontal, not horizontal, inclined surcharge plus for strips also. Now I have only done for GeoGrid. I have to do it for geo strips also. तो ये सब combinations मुझे डालने हैं plus उसके beta testing करके validate करना है. So I may need another 2 months or so. उसके बाद मैं आप लोगों से जब ready हो जाएगी तो share कर लूँगा. Irison की website पे डाल दूँगा. I put all my programs on Irison website. Okay. Right. Thank you then for